Hello. Today we are going to talk about stereoscopic mixed reality, meaning virtual reality plus augmented reality in UAV search and rescue missions. Let me introduce Team Armet. We are a part of 4 years Gemstone program which fosters selected undergraduate students to pursue 4 years of research. And we are a team of 12 undergraduate students and a mentor, including aspiring engineers, computer scientists, physicists, and mathematicians. Team Armit focuses on improving search and rescue missions using UAVs. Disaster areas pose great threat to both victim as well as search and rescue teams. And in recent development in UAVs made it possible to aid in search and rescue missions, as it can reduce search time because UAVs can survey a wide range of area in less amount of time and thus saving the search time, and also reduces the human interactions in hazardous environments. We are incorporating head tracking synchronization, stereoscopic vision, and overlays capabilities to improve the pilot's situational awareness, which in turn will aid search and rescue missions.
Here's a more detailed overview of our system. A virtual reality headset, the commercially available Oculus Rift, gives us head tracking data in the form of Euler angles for the pitch, roll, and yaw of the user's head. This data is sent through the existing telemetry link used to control the UAV via MAV link to the gimbal controller mounted on the UAV. The controller then rotates the gimbal motors in synchrony with the pilot's head, independently of the UAV's motion. Lastly, the videos from the cameras on the gimbal are streamed live to the Oculus Rift. The transmission is performed with a set of two dedicated video transmission systems made by Connex, which can provide 1080p 60 fps video wirelessly with low latency in line-of-sight environments. The videos are distorted with a barrel distortion to account for the pincushion effect of displaying a 2D image in 3D. Lastly, augmented overlays are added to assist the pilot with the search and rescue mission.
In this slide, I'm going to talk about how we implemented head tracking capability. As a user moves his head up and down, the data from the Oculus Rift is extracted in Euler angles in X, Y, and Z sequence and linearly interpolated with PWM signals, also known as pulse width modulation. Later, these signals are fed into the gimbal controller to sync the head movements of the user. The graph to the left is the output of Oculus user's pitch head movement, and to the right is the output of pitch from the gimbal controller. Both graphs match, indicating that the gimbal is in sync with the Oculus head tracking.
We have also implemented augmented reality overlays, which displays relevant flight information, such as the altitude, the speed, the mission time, on the stereoscopic feeds. We have placed a placeholder image on the bottom right here, where an image of the search objective can be included for the search and rescue pilot to use as a reference during the mission. You may have also noticed the weird shapes on me in the picture. We have also implemented some basic human detection algorithms in the form of Parlake feature-based cascade classifiers, so our computer can identify and highlight them for the pilot. Having this eliminates the necessity for people to be analyzing the video feeds at a separate ground control station, allowing the search teams to focus on other tasks.
In this video, we are going to show our product in action. As you can see, the user moves his head in omnidirection, and the gimbal, which is on shelf and is custom made with the GoPros in it, is in sync with the head movements that the user makes. And the user sees the stereoscopic vision with overlays rendered on the stereoscopic display. We also did a transmission test using a Connex system, which, since we cannot fly our UAVs inside the laboratory, so we carried our gimbal handheld with the Connex transmission system and outside the laboratory, and we were able to transmit the stereoscopic videos in real time and wirelessly. And because of due to the limitations and no line of sight of the Connex, we could only able to go limited distance.
To test depth perception between stereoscopic and monoscopic vision types, we implemented a simple cylinder test. It consisted of two cylinders, one stationary on the right, and one controlled by the participant on the left. The test participant would attempt to align the two cylinders as closely as possible, and the distance between the cylinders would be the result of this test. We conducted this test 3 times in each vision type, both monoscopic and stereoscopic, and the mean value was taken as the measure of the test.
Here are the results of the cylinder test. As smaller values indicate the cylinder controlled by the participant was more closely aligned with the cylinder on the right, lower values are better than higher values. As you can see for the first half of our tests, we report that monoscopic vision tests did much better than stereoscopic vision. However, this could be attributed to the method of testing, because during the monoscopic test, the participants were able to move their head closer to the screen arbitrarily, allowing them to be more precise with their alignments. However, during the stereoscopic test, it was imperative that the person taking the test was placed between the two sensors of the Oculus Rift properly, so that the axis that they were looking down and the axis shown on the computer screen through their HMD was aligned. We didn't pay attention to this during the first half of our trials, which probably explains why there is such a discrepancy between stereoscopic and monoscopic vision types for this part of the test. However, as this was adjusted for the latter half, we can notice that the stereoscopic and monoscopic had very similar results for depth perception. We also created a virtual obstacle course to serve as a test for our system, where the user would fly a virtual drone through a 3D environment, dodging obstacles and navigating through waypoints. As our metric for this test, we tracked the collision count of our test participants and evaluated that. Again, we performed this test with both mono and stereoscopic vision, where monoscopic vision, we had the user just looking at a computer screen with a UAV controller in their hand. And with stereoscopic vision, we had them look through using our HMD system, in our case, the Oculus Rift, where they could turn their head independently of the UAV motion. And the results of this test are given in this plot. We can see that consistently, the testers performed better in the stereoscopic trial than in the monoscopic trial, likely because they were able to look for obstacles in their environment without turning the entire UAV. In the monoscopic trials and in current control schemes, the pilot must turn the entire UAV to look around their environment. With our system, this can be done independently from the motion of the UAV, allowing for greater situational awareness. In summary, we've shown that the depth perception obtained from stereoscopic vision and monoscopic vision are basically indistinguishable from each other. However, collision avoidance was way better with stereoscopic vision through our system. And this is likely because VR allows for an easier view of the surroundings, granting us greater situational awareness. Now, during the testing, we experienced two major difficulties, the first of which was our testers experiencing VR sickness, which is similar to motion sickness because their input was often not matched with the output that they expected. And this is likely due to our second problem, which was the difficult controls that we had to implement to create our 3D environment for our obstacle course. Ways to extend our research include implementing a better human detection algorithm than the one that we have used in the form of fragmentation, as shown by the image on top. It is also possible to implement more sensors into our payload, such as an IR sensor, which would assist with human detection. And it may also be of interest to look into creating an aid kit drop, where the payload would be able to deliver first aid and like objects to the victim as they wait for a search person to get to them. In summary, we've built a custom gimbal to implement our head tracking algorithm. We've fed in a stereoscopic video feed to our virtual reality headset. We've implemented augmented reality overlays in the form of human detection. And we've successfully implemented head tracking synchronization with the user's head. We have also created a few flight simulations to test our system. We would like to thank the Institute of the Physical Sciences and Technology, the Laboratory for Computation and Visualization, as well as our mentor, Dr. Anil Dean, and an advisor, Dr. Huan Zhu, for assistance with our project.
Thank you.